I want you to imagine waking up tomorrow to discover your compass points south instead of north. You'd probably think you were dreaming, but is that really possible or is it totally impossible? Actually, it might surprise you to learn, it's actually inevitable that something like that could actually happen. Right now, at this very moment, deep beneath our feet, a battle of sorts is brewing in Earth's molten core, one that could actually flip our entire planet's magnetic field, magnetic poles, upside down and sort of be reversed from where they are today. And I mean that quite literally. So pole reversals on our planet have actually happened hundreds of times before, and the evidence is literally written in stone across the entire planet. Now, this has actually interested me for a long time personally, but a big question that I always had is what actually triggers these massive reversals in the Earth's magnetic field? What is a magnetic field anyway, and why do we care that our planet even has one? And if it reverses, what would actually happen? And our magnetic field actually has been weakening by a whopping 10% in just the last 2 centuries. Could we be on the brink of another one of these flips? And if it actually happens, what's going to happen to everyone on the ground? Digging a little deeper, what actually happens during a magnetic field flip? And is it actually dangerous to life on Earth? Do we have anything to actually worry about, in other words? Or would it interfere with our technology, right? So I'd like to start a journey through our solar system where magnetic fields tell a story of planetary life and death. So since we're starting with magnetic fields and reversals, let's first start with our sun, because our sun actually has a massive magnetic field that's constantly churning and constantly changing. In fact, most people don't know this, but our sun has a magnetic field that actually flips every 11 years. It actually goes south to north, north to south every 11 years like clockwork. It's about twice as strong as the Earth's magnetic field at its surface, but the real powerhouse in terms of magnetic fields in our solar system is actually Jupiter. So the gas giant Jupiter has a magnetic field about 14 times stronger than Earth's, making it the strongest in the entire solar system. It might be a little counterintuitive actually when you think about it that Jupiter is so much bigger than Earth, has a field about 14 times stronger than Earth, but the sun is even bigger than Jupiter and doesn't have a field at its surface as strong as Jupiter. Well, it's a little bit tricky. I mean, it is a little bit interesting to talk about that because the diameter of the sun is much, much, much larger than Jupiter. So when I say the magnetic field of the sun at its surface is, however, 2 times or whatever it is of the Earth's magnetic field, you got to remember that that's at the surface of the sun. If you went inside the sun to like an Earth radius, because the magnetic field usually gets weaker as you get away from the body. If you go inside the sun to a diameter of a core of the sun, of the Earth, then the magnetic field strength will be totally different. So we're comparing across planets and stars, but at different radius from the center is what I'm trying to say. So the fact that it's only 2 times stronger isn't so surprising because the diameter of the sun, and we're measuring it at the surface, much farther away from the center. And actually, another interesting thing is Jupiter has such a strong magnetic field that the magnetic field from Jupiter trails Jupiter very, very, very far with the interaction of the solar wind coming out of the sun. And it actually influences the magnetic field of our solar system, kind of like the magnetic environment of our solar system, all the way out past the orbit of Saturn. So Jupiter is critical for our solar system, not only because it's a very large body and it's kind of like sucking in debris gravitationally, comets and other things, protecting the Earth from being bombarded as much, but the magnetic field is also influencing everything in the outer solar system. Now, moving out beyond Jupiter, Saturn actually has a magnetic field slightly weaker than Earth, which actually really surprised me. But then you go past Saturn to Uranus, and that has a magnetic field strength about 10% of the Earth, so again, pretty weak. But then Neptune reverses that trend and has a magnetic field much, much stronger than Earth. So those are the outer planets, right? You have weak and then you have very strong magnetic fields. Now, if we go the other way to the inner solar system, Mercury has a tiny magnetic field, about 1% of the Earth's magnetic field strength. Venus and Mars, well, those are the odd ones out because they have almost no magnetic field at all. And what about our moon? It's our closest neighbor. It's right there. It's got no significant magnetic field today, though evidence actually suggests from looking at the Apollo moon rocks and other landers that it might have had a very substantial magnetic field billions of years ago. So let's back up the truck for just a second and ask the question, what exactly is a magnetic field, and why should we care anyway if our planet has one or doesn't have one? So I want you to picture an invisible shield surrounding our planet, kind of like a starship, shields up, something like this. So this magnetic bubble is also called a magnetosphere. That's the big word for it, magnetosphere. And it protects us from harmful solar radiation and cosmic rays. Quite simply, without our magnetic field, our atmosphere would slowly be stripped away by the solar wind, kind of like what actually already happened on Mars. So obviously the main question in the video is, when is the next pole reversal on the Earth going to happen, and is it going to hurt us? So we're kind of taking a detour here to understand what the consequences of not having a magnetic field is. We don't think about it all that much because we live on the Earth and we go about our everyday life, but actually we live in a really, really inhospitable environment. Basically, the sun, who's also keeping us alive with energy and warmth and things like that, is basically constantly trying to kill us all the time. And what I mean by that is the sun, through the nuclear fusion, it's sending out photons, light, particles of light, or you want to think of it as waves, that's fine. But it's also sending out solar wind. And that means it's constantly streaming out from the nuclear reactions, protons, naked protons flying through space, electrons not bound to an atom, naked electrons, ions, which could be, helium nuclei, things that are stripped of their electrons, but ions flying out into space. And basically this going in all directions. And Earth is relatively close to the sun. So when these solar wind particles come out at thousands of miles an hour and hit our atmosphere, what do? They excite the electrons in our atmosphere. That's what causes the auroras, the beautiful light show that we see. Basically, when you have a magnetic field and you have a charged particle like an ion or electron coming in from the sun, we can do this in the lab, we can see it in space. The charged particle or the ion, it gets trapped in the magnetic field. Basically, it starts to orbit the magnetic field lines, and they often bounce between the poles of the Earth while they're orbiting our magnetic field lines, and that's, again, what causes our aurora. But the bottom line here is they get trapped by our magnetic field from the magnetic forces acting on charged particles moving, right? But without a magnetic field, all that's going to happen is that solar wind is going to smash into our atmosphere. It's going to excite the electrons, causing, a lot of light to come out. That's what the aurora is. And over time, it's basically going to break down our atmosphere, and we're going to slowly lose our atmosphere into space without a magnetic field. In fact, that's what we actually think happened on Mars. The atmosphere of Mars is very, very thin. We know that there used to be a lot of water there. We suspect there was a magnetic field on Mars in the past, and look at what it is today. It's a great planet, it's big, but it has really not much of an atmosphere to speak of. And so the concept of living on a planet with no magnetic field, like the moon or Mars, is going to be challenging because solar wind is going to be hitting us all the time. And that's why when we go to those planets, we're probably going to have to build bases at least partially underground, because the ground actually, can absorb and stop a lot of these particles as well. So that's kind of the big deal with not having a magnetic field at all. We basically will eventually lose our atmosphere. Now, I just touched on this, but let's go in a tiny bit more detail. Mars and the moon don't have a magnetic field. Why don't they have a magnetic field? Well, Mars was much more Earth-like in the past. We can see the river valleys and things on the surface. It had a magnetic field potentially as strong as the Earth's about 4 billion years ago. So what actually happened? Why did the magnetic field go away, which causes the atmosphere to go away? That whole chain reaction, why did that happen? Well, the current data points to a case of planetary downsizing, so to speak. Mars is really just too small. It's only about half of the Earth's size, and so the core of Mars cooled off much, much faster. And it's not totally cool today, but it's cooler than the Earth's core. And as the core temperature drops, the liquid outer core in the planet's center, they're likely solidified. And that shuts down the dynamo effect, we're going to talk about a lot more detail in a second, that actually generates the magnetic fields in the first place. And without the protective shield I mentioned, the solar wind gradually strips away most of Mars's atmosphere, and that transforms it from what it once once was, which was kind of hospitable and wet, into a cold, dry world that we see today. Now for the moon, the story is actually a little bit different. Moon rocks, which are brought back from the Apollo astronauts, show signs of an ancient magnetic field that existed until about 3.2 billion years ago. And so the leading theory here suggests that the moon's magnetic field was powered by a very unusual dynamo effect. Instead of convection like the Earth, the early moon's liquid core was stirred by the Earth's motion, kind of like swirling coffee in a cup and you're kind of dragging around the creamer as you go and things like this. But as the moon's orbit slowly moved farther away from the Earth, this stirring effect weakened, and so that changes the inner dynamics of the molten core moving, and so the core wasn't as hot and it wasn't molten enough to maintain the magnetic field that the moon once had. This is not quite the same thing, but very similar because Jupiter has a moon called Io. It's the most active volcanic moon in the solar system. Jupiter is way far away, farther from the sun, and so Io should be really, really cold. Why does Io have all of these liquid volcanoes erupting magma all the time if it's so cold out there? Well, the reason is because Jupiter is massive, and as Io is in the orbit fairly close to Jupiter, orbiting Jupiter, it's flexing its crust all the time just from gravitational, getting a little farther away, a little closer, gravitational flexing of the crust as it orbits over and over again. And the friction from that gravitational flexing is where all of the heat is really coming from in making the center of Io molten enough to be so volcanically active. Now let me just say one thing that's on my mind that always blew my mind, really. You know, Earth's been around for billions and billions of years. And if I take a hot, molten, red hot poker, let's say, put it in a campfire red hot, or even if I melt some iron or something like that, and I put it on the, in the environment, it's going to cool off. It's going to be red hot, then it's going to become not so glowing, and then it's not going to glow at all. You're not going to see it, but it'll still be hot. But eventually it'll cool to room temperature within, I don't know, an hour or something. It'll take some time, but it'll cool off. How is it possible that the Earth has a core that is still molten after billions and billions of years? Don't you think it would have cooled off by now? Well, this is one of those things where our human brains can't really, in my opinion, really contemplate or really comprehend. First of all, the Earth is probably bigger than you can imagine. It's a huge amount of mass, right? And also, how can the energy ever leave the Earth? You see, with the red hot poker in the campfire, when I take it out of the campfire, it's touching the air. It's very hot and it's heating up the air molecules, and so the air molecules, fly away. It takes the heat away. It convects, or conducts is a better word, the heat away from the red hot poker. But for an entire planet, you have the core and you have the crust, so everything's touching, right? And then you have the atmosphere, which is touching the crust, but then outside the atmosphere, you have nothing but space. So how could heat ever get away from the center of a planet? Well, it'll conduct all the way through the crust and, kind of like make its way to the surface. But once the heat eventually makes its way to the surface, how does it get away from the planet? There's no air outside of our atmosphere. I mean, even if it conducted through the atmosphere, eventually it reaches vacuum. There's no atoms in there, not enough to conduct the heat of the planet away. So how does the planet ever cool off? Well, the answer is the main way that you get rid of heat is conduction, which you've heard about, convection, when you have the water going up and down when it gets hot and cold, and radiation. So what happens is there's no air or matter outside of our atmosphere to conduct anything away. So the only way that the Earth or any planet can get rid of its heat is through radiating photons. And when you look into the physics there, the radiating of photons takes a really long time to carry the heat away from a planet. It does cool off, just like Mars cooled off, but it takes a long, long time, right? So I just always found that fascinating. You would think that after billions and billions of years, the center of the Earth would be, like pretty chill because it's been a long time. But actually, there's no really good way to get rid of the heat. So the planet has stayed hot for a long, long time. In fact, when you go into a cave, like I've been in a cave, it's pretty chilly in there, like just, 20 meters underground or something. It's pretty chilly in there. But if you actually drill, and people do this, you drill down a couple of kilometers down from the crust of the Earth, it's already starting to warm up. It's not molten or magma down there or anything, unless you're in Hawaii somewhere. But even without magma being nearby, it gets warmer pretty fast once you get past the crust of the Earth, and eventually gets much hotter when you get deeper. Now, let's get back to the pole reversing of the magnetic field, because I think this is where it actually gets really interesting. We found evidence of past magnetic field reversals written in stone on the Earth, and I do mean that quite literally. You see, when volcanic rocks form, these tiny magnetic materials inside the rock actually are aligned with the Earth's magnetic field. That's how magnetism works. And when everything's kind of molten, things can kind of line up. But when it cools off, they freeze in place like a frozen compass, pointing in the direction of the magnetic field when that rock formed. Now, scientists have found rocks, many rocks, with magnetic minerals pointing in opposite directions over time in different layers. This way, pointing this way, this way, this way as you go deeper. And that shows us exactly when these magnetic field flips occurred in our past. And you can see it even more in the ocean floor, which tells an incredible story. So as new seafloor forms at the mid-ocean ridges, right, when it comes up and solidifies and pushes things apart, the plates, it records the magnetic field orientation at the time when it comes up and solidifies. And so what that does is it creates a pattern of magnetic stripes, for lack of a better word, on the seafloor that kind of, if you use your imagination, would look like a cosmic barcode. In other words, the magma comes up and it kind of like gets cool from the ocean water, and it's aligned with the magnetic field this way, and it freezes, right? Over time, more of it comes up. If the magnetic field of Earth is flipped the other way, it freezes in a magnetic orientation opposite and opposite and opposite. And as the seafloor spreads, we can literally look on the floor where the magma go, 50 meters that way. You can see the magnetic field of Earth flipping back and forth with great regularity. Now, scientists have been collecting this evidence for decades, and based on this evidence of looking at the seafloor, we know that the Earth's magnetic field has flipped hundreds of times over its history. The last major reversal happened about 780,000 years ago. And actually, even though that sounds like a huge number, in geologic time, you're usually talking in millions or even hundreds of millions of years. So 780,000 years is long to humans, but it's really nothing in geologic time. So we can see that the reversals of the field have happened with some sort of regularity, but it's not like a clock. It's not like, okay, it's time to flip today. They've happened as frequently as every 50,000 years over the geologic record, or as rarely as every couple of million years. So we don't know exactly, when the next one will happen, but we have a good idea based on the intervals from the past. Now here's a wild fact. These magnetic field reversals are actually pretty slow. You might think it's a really rapid process, but on Earth it seems to be pretty slow. The whole process of flipping the magnetic field seems to take about 2,000 to 12,000 years. So it's really not like flipping a switch, it's kind of a gradual changing. Now we don't really know if it's slow, and then a little bit more rapid and then slow. We don't know exactly that granularity because we're looking at rocks after all. But we know that it's not just like on Tuesday morning it flips. We know that it doesn't happen like that. Now it's interesting to compare this to the sun, which I already told you, the magnetic field of the sun actually flips every 11 years, and that is kind of like clockwork. I mean, plus or minus a little bit. But the flip on the sun actually takes a few months to occur, and in some cases a couple of years to flip. But it's within a band of uncertainty, it's a much more rapid process than what we see and think that the Earth actually experiences when it flips. Now, one thing I've always been curious about is, did these magnetic field reversals on the Earth cause any mass extinctions? Well, good news, there's no clear evidence linking magnetic field reversals to any major extinction events that we see in the fossil record, because we do see a lot of them, but they don't seem to be lined up with these magnetic field flips. So though the field weakens during a reversal, it never really completely disappears, and then it stabilizes in the new orientation. Now I'd like to talk about what really fascinates me personally, being the nerd that I am. How does the Earth actually generate its magnetic field in the first place? Might be a good idea to know how that happens, to see how it happens when it's going to flip, right? So I want you to picture the Earth's core as a giant generator, like you might see at a nuclear plant or a hydroelectric plant, turning all the time. So in our case, we have a solid inner core, which is made mostly of iron, but that's surrounded by a liquid outer core that's also rich in iron, but also nickel. Now, the outer core is super hot. It's around 4,000 to 5,000 Celsius. That's around 7,000 to 9,000 Fahrenheit. And as I mentioned before, it takes a long time for a huge body like this to get rid of the heat and cool off, because the only way it can happen is from radiation from the surface into space. Now, here is where it gets really interesting in my opinion. The liquid metal in the Earth's outer core, it's not just moving around, it's actually conducting electricity. That's the part they don't usually tell you when you're learning about this stuff in grade school. You see, when metals, like the iron and the nickel in the Earth's core, get super hot, their electrons become more loosely bound to the atoms, and that allows them to flow more freely. The iron and the nickel in the Earth's outer core are so hot that they're in a special state where electrons can almost move as freely as they do in a copper wire. So you can really think of the core of the Earth with the liquid molten metal and all that almost behaving like a plasma at these extreme temperatures. Just an aside, that's why metals like, copper, silver, gold, why they conduct electricity in the first place. Metals conduct electricity generally, and non-metals like carbon or, whatever plastic, generally don't. It's because of the electrons that are in the outer shell of those atoms. And we could go into a whole lot of theory, but basically those electrons are not held on as tightly by the nuclei of those metals. And so they're kind of free or more free. They're bound to the atom, but when you put a bunch of them together, they can exist kind of as in a state where they're a sea of electrons that can be easily pushed around. Now, when you take a metal like that, which already can conduct electricity, and you heat it up, then what actually happens is those electrons that are very weakly bound to the metal there, they can kind of separate and kind of flow freely. In other words, they literally can be separated from the atom, and that's what a plasma is. A plasma is basically a situation where you have some matter and the electrons have been pulled off by some mechanism, in this case it's heat, and they're kind of mixed around in a soup of ions from the atoms and electrons which are freely floating around. When you have a soup like this in sort of a plasma state or a semi-plasma state like in the Earth here, then it behaves like an electrically conducting liquid. So it's not just that there's molten metal, because that wouldn't really conduct electricity or generate a magnetic field. Magnetic fields come from moving charged particles. That's how a magnet works. A permanent magnet works because the electrons are spinning and aligning with their spins in such a way that they all align up, and we see the magnetic field. It's motion or movement of those electrons in a spinning state. If we push electrons through a wire, like with a circuit, then it also generates its own magnetic field, again, moving electrons. In the Earth, you have this gigantic electric conducting liquid, and it's constantly moving because the Earth's rotating, and so that is the theory basically of how the magnetic field of Earth forms. Now, diving in a little bit deeper, this electrically conducting fluid is constantly moving due to two main forces. First, it's convection from the intense heat, like when water boils or a gas gets hot, and then because it's hot, it's less dense, so it rises. But then it cools off, and so it's more dense, and so it falls. And so you have this constant convection. That's always happening inside the Earth. But you also have something called the Coriolis effect from the Earth's rotation. It's pretty easy for us all to visualize the Earth rotating and kind of like dragging around an inner core. Think about an egg, like just an egg you might buy. It's got a hard outer shell like our crust, but it's got a yolk in the center, which is gooey, right? If you spin the egg, you can imagine that on the inside, the surface of the shell is dragging around the kind of gooey center. And it's not stuck to it like a hard, rigid solid, it's dragging it around. But it's a little bit more complex in the case of the Earth because the Earth is so big. You see, if you have the Earth there, when it's spinning on its axis, if you're standing on the surface of the Earth at the pole, you're rotating around, right? But you're not moving too fast because you're right on top of the pole. But if you're down by the equator, you're moving at like, 1,000 miles an hour, something like that at the equator because you're way far away from the pole and the Earth is still rotating and you're riding on the surface of the Earth. So if you're just inside the crust near the equator, you're dragging this magma with great force. But near the pole, because you're next to the axis, you're rotating around the axis and there's not much of a dragging force. So there's a difference in the forces just inside the crust and also near the center of the Earth, just because the Earth is a sphere and the rotation velocities are different when you're near the pole up there and also near the equator. That's called the Coriolis force. Now, on the outside of the crust, that Coriolis force is what causes, ultimately, along with heat from the sun, hurricanes and tornadoes, because that dragging force can turn a lot of convective activity into a horizontally rotating structure that's very large, like a hurricane. But on the inside of the Earth, we don't see the hurricanes, but we know that it has to be moving with some crazy rotation because that's the only way magnetic fields can be generated. So that Coriolis force along with the convection is why the inside of the molten state of the Earth is always moving. Now here's the part where it gets a little bit more complicated, but we have to get through it. I think it's really interesting. When a conductor, like this molten metal, is moving through an existing magnetic field, it generates electric currents. So that's basic electromagnetic induction. So there's two things going on here. You have the moving metal, which is a plasma state. It's generating a magnetic field. So there's a magnetic field there because of the charged particles moving. But then, because that magnetic field is there and other charged particles are moving like electric current through there, then what you basically have is you're generating electric fields and magnetic fields because of the churning action here. Let me say that one more time because it's crucial to all of this stuff, crucial to the instability of our magnetic field. So you have the Earth rotating. That's a mechanical force that's moving this liquid in there. That liquid is a charged liquid. So it's like electricity in there. That's generating a magnetic field, right? But then what you also have is when you have a metal moving through a magnetic field, it generates an electric current. But don't forget, electric currents also make magnetic fields. So it's like peanut butter and jelly just kind of continually influencing each other. That's why plasma and nuclear fusion and fusion rockets, it's very, very complex to study because what you have is moving electric currents generating magnetic fields, but then the magnetic field is there, and then you have other charged particles moving through the field, and it generates an electric field, which generates more currents, which also generate another magnetic field. So it's a feedback loop that's very difficult to calculate. You can't really write a single equation down and solve it for the answer because it's a very complex interaction of multiple things influencing each other. And ultimately, that's what's going to lead to the instability that causes our magnetic field to flip. So the core question is, why does the magnetic field flip and why does it take so long? And this is where we get into theoretical territory because we don't have great models for this, right? We don't have single equations we can solve. So scientists believe it's basically related to irregularities in the flow of the liquid iron in the outer core. Computer modeling actually suggests that when the flow patterns become sufficiently complex with eddy currents and other vortices that are happening on the inside, they can become chaotic. And that causes the magnetic field to become unstable and eventually reverse. Because remember, it's a complex interplay. You have a moving charged liquid generating a magnetic field. Then you have other parts of the conducting liquid which is moving through the magnetic field that's there, and that's causing an electric field which pushes on everything in very unpredictable ways. But eventually, if the eddy currents or instabilities become great enough, it can destabilize the main field that's present and eventually lead to an unstable situation which causes a reversal, and it stabilizes in the other direction. You can kind of think of it as a cosmic game of tug of war, sort of, between magnetic field loops in the outer core. Sometimes one configuration wins out over the other, leading to a complete reversal and a long period of a stabilized magnetic field. But I should emphasize, while we understand the basic physics, I mean, we know about induction, we know how magnetic fields are generated, we know this stuff, the exact trigger mechanism for the reversals themselves is actually still debated, and the details are being studied. One mental image you can have in your mind is, have you ever looked at one of those plasma balls that you might get from the science store? You know, it's very pink and purple and they're beautiful, right? When you look at that plasma ball, it's very, very beautiful and you can see the tendrils coming off and touching the glass, but it's by itself totally unstable. Even if you're not touching it, you can see it whirling and churning and kind of like snapping in different positions. And just look at one of those things. They're not a very stable thing. They're always moving. It's the same thing going on in there. You have a plasma, and so the gas is ionized, which means it's carrying electricity. When the particles begin to move, that generates a magnetic field. But then the magnetic field, whenever the charged gas moves through it, generates an electric field, which generates an electric current, which generates another magnetic field, which pushes it in another direction, and so on and so forth. So the process keeps feeding back on itself in this weird, chaotic way. And you can see in a plasma ball, that's a tiny little thing, how unstable that is. Imagine some gigantic ball moving of this kind of plasma-like fluid under our feet. That's the kind of complexity we're talking about here. Now let's get to the point of the matter. We might be due for another reversal of our magnetic field soon. the Earth's magnetic field has actually weakened by about 10% in the last 2 centuries, the last 200 years. And we've spotted a giant weak spot in the magnetic field of Earth called the South Atlantic Anomaly. So I can tell you something about the South Atlantic Anomaly because I used to work on the space shuttle in mission control, and I was actually working on the computer systems for the space shuttle, monitoring all that stuff during all phases of flight when the space shuttle was in orbit. Now, the shuttle was one of the first, well, definitely the first spacecraft, but one of the first flying machines to really have onboard computer systems. So it had memory, just like your smartphone has memory. Now, when you take a computer, a phone or a shuttle computer, and you go up into space, you're getting a little bit farther out of the magnetic field, of our protective magnetic field. And so the solar wind is coming in, and it's constantly coming in and hitting your memory in your computer. And that solar wind is like, it's basically radiation, and it can flip bits in your memory from a 1 to a 0 or a 0 to a 1. And that can happen all the time. So the space shuttle had a very sophisticated memory scrubber that was always running, and it was always checking what was happening with the memory, and it could detect a certain number of bit flips in a single byte of memory, and it could flip it back automatically to the correct value if a cosmic ray hit it. And we would monitor those bit flips all the time on the ground. Now, we would see them all the time. We would see 1 or 2 flips with every 10 or 15 minutes, we would see them all the time. But there's this region of the ocean called the South Atlantic Anomaly where the magnetic field of Earth is a lot weaker, maybe because we're about to hit a pole flip, right? And when the shuttle would fly through those, you would see 50 bit flips within 10 minutes or something like that. Maybe not 50, maybe 20, but a lot. It would be like 10 or 20 times what we would see any other place on the planet, like clockwork. This region was, I don't even know how many square kilometers. It was a fairly large part of the ocean. We would fly through it every couple of orbits, and we would see it over and over again. So, could this be the start of another one of these magnetic field flips? Are we witnessing right now a field flip in progress, happening really slowly? Remember, they might not take 1,000 years to complete. Remember, the average is 300,000 years between these flips of the magnetic field, and our last one happened over 700,000 years ago. So we might be overdue. Only time will tell. I want to thank you for hanging out with me today. I like chatting with you about these things. I'd like for you to please drop me a line, leave me a comment, send me an email, let me know what you think. Do you like more of this stuff, less of this stuff, more detail, less detail? And as you think about the magnetic field of Earth, as you ponder, is it going to happen? What's going to happen when the field flips on the Earth? I want you to always look up at the sky and remember to always stay curious. Learn anything at mathandscience.com.